Okay, welcome again to an OpenStack Astronomy short video lecture. Here we'll be looking at chapter 26. Oops, there we go, chapter 26, and we'll be looking at galaxies. And so here we have an image of just a couple of different spiral galaxies here. Again, much like our Milky Way galaxy, we talked about that initially, and now we could start making inferences on other galaxies. So galaxies and cosmology, as we had mentioned before at the end of the last video, is that if we want to study the structure of the universe, we want to look at some fairly large objects. So looking at individual stars is too small of a scale. So what we look at is at galaxies. That kind of ends up being the smallest piece that we could look at and follow how they have evolved. And so the study of galaxies really gives us insights on the structure and evolution of the universe. So how they formed, how they get grouped together, what their motions are, and, what their kind of the structure is of them. So studying those really gives us an insight on the structure of the universe, which is cosmology. And so we'll look at three different types of galaxies here. There are spiral galaxies, like our Milky Way galaxy that we looked at. There are elliptical galaxies, and then irregular galaxies. So spiral galaxies we looked at in the last section, but just to recap here, there's the bulge in the center, very dense. You have the halo, which is kind of this sphere around with typically old globular clusters there. And then you have the disk, which is where the spiral arms are, and you have ongoing star formation there. And here is an edge-on view. And so you could see the bulge and then the spiral there. We're on the outskirts. So if the sun is kind of on the outskirts of the Milky Way galaxy, so when we see that Milky Way, that haze in the night sky, we're looking kind of edge on towards the galactic center. Here's another image, kind of side view here. Again, the spherical component, the bulge in the center, and then we have also the halo, right? On the outskirts there of old stars, and then the disk component. Bluish in color, again, indication of ongoing star formation. Elliptical galaxies, they're more spherical. They don't have that disk component, and they're typically more red, yellowish in color, again, indicating an older star population. Here are a couple images of elliptical galaxies here. And so you could see, again, one is a bit more elongated here on the left. And then on the right there, kind of spread out a little bit, but again, doesn't have that disk and that spiral component to it. And we see here on the image on the right looks a little bit more bluish in color. And so what we believe is perhaps that is a merger of two spiral galaxies that had collided. So stirred up some of that dust and gas and created a bit of some of that new star formation there. We also have lenticular galaxies here, which is kind of a blend of the elliptical and a spiral, kind of an intermediate between the two here. So you could see elliptical in shape, but then that disk kind of around the center. Here's an image of classifications for galaxies. You could see ellipticals ranging from E0 all the way up to E7. And the higher the number, the more elongated it is. And then spirals, you have the barreled spirals and then the unbarreled as well. And then again, around that SO would kind of be that merger of ellipticals and spirals. And then we have our third classification is irregular galaxies. So neither elliptical or spiral here, but they do have kind of blue-white color, indicates again ongoing star formation here. So what about evolution of galaxies? So how these could kind of develop here. So we see that spiral galaxies are often found in groups of a few dozen. So not so densely populated when we look at spirals. As opposed to elliptical, when we look at clusters, we see hundreds to thousands of them. Again, more densely populated, a lot closer together. If we do a census of the night sky, again, looking out deeper into space, we end up looking further back into time. And we see that further back, we have younger galaxies are irregular. And then it takes some time for, I guess, them to get their structure. And then you see probably at about 5 billion years or so, from the Big Bang, you'll start looking at ellipticals and spirals, galaxies that tend to form. And we still have a few irregulars there, again, because of ongoing collisions, things of that nature. And so the conditions for the protogalactic cloud here is really the spin that determines if it becomes elliptical or if it becomes a spiral. So if you have kind of more, that angular momentum is going to give you more spin, and it's going to flatten that disk out, creating a spiral. Versus if it's kind of more stagnant, slowly moving, you're going to keep its spherical shape, and you're going to have more of an elliptical galaxy there. If we're talking about evolution of galaxies, we also have to consider collisions, right? So how do collisions actually affect them? Things are attracted to each other by gravity, so that plays a big influence here. And actually, we see, let me go back here. Here we see an image of two spiral galaxies that are merging together, and we actually see from computer simulations that two spiral galaxies will eventually merge into an elliptical galaxy. So the universe right after the Big Bang was more dense, a lot smaller, so a lot more collisions, hence the irregular galaxies that we see early on. So they weren't able to kind of form their shape. And as time went on, more space between them, you were able to now get the spiral and those elliptical galaxies to form. And so we see that early on, 2 to 4 billion years, irregular galaxies, and even up to 5 to 7 billion years, right? Again, early on, more dense. You're going to have a lot more collision within these galaxies. They're going to be much more crowded. But we see some even, up to about 7 billion years that are still violently disturbed there. So meaning that still ongoing collisions are occurring. Here is a computer simulation of two spiral galaxies merging together into an elliptical galaxy. So they would be attracted, gravitational pull will distort it, and then the end result would end up being in elliptical. And this probably explains why spiral galaxies are found in few dozens. There's more space between them, not so much collisions, versus ellipticals. It's if spirals are going to collide, if it's more densely populated, you're going to end up with more elliptical. So that's why you see those clusters in the hundreds or thousands. And so here, again, looking at these elliptical galaxies, those collisions explain why these are highly dense, right, populated. Here you'll see these the ellipticals with many of them because they are having collisions, and you don't see very many spirals because if they collided, they would turn into ellipticals. So when we talk about distance, we're kind of going further back in time. And so we want to figure out exactly, well, how far back, right? What are the distances of these galaxies here? So we talked a little bit about this in the last module about radar or parallax and then even main sequence fitting and with supernovas. But to talk about objects that are very distant, we have to look at Hubble's law. And so Hubble's law has a relationship with the distance and velocity and with the redshift of galaxies. So when we look at these distant galaxies, not only are they moving away, but they are moving away at a faster rate. So the redshift on them is larger. And that actually indicates or gives evidence for the expansion of the universe. We see these relationships here again, as we said, further distance, the higher the velocity. So these are increasing right at a larger rate as we go, as we look further out. And so this gives rise to evidence of the expanding universe. As the space between galaxies increases, right, that space itself kind of just stretches out, you'll see that the space between them will get larger. So galaxies, no matter where you're at, are always going to appear that every object is moving away from you. And the further out, the more of a redshift it's going to have. So as time goes on, the universe expands and the distance between these objects gets larger. So the universe looks about the same no matter where you are within it. So there is kind of no center, no edge. From everyone's vantage point, it's always going to appear like if you're in the center, because you'll see other objects moving away from you. You don't really detect your own motion. So since we have the expansion of the universe here, objects are moving around. It makes it a little bit difficult to kind of keep track in terms of where objects are. So for example, if we are looking at a galaxy, right? So here's a galaxy and it sends some light beams that we actually tend to capture today here. Well, that light left a long time ago. And so when we get that light, that galaxy is no longer there. That galaxy has moved position somewhere else. So we not only see that galaxy how it looked like some time ago, we also see at the position that it was. So as we look at objects that are further away, we tend to rather think of them as looking back in time. So rather than distance, we think about it as time frame. So the further out we look, the further back in time we're able to see. And so that's helpful because it gives us a nice kind of overall picture of these galaxies. So when we're able to look at distant galaxies, these irregulars that are older, we're looking back in time to how galaxies were evolving at an earlier time. And now currently we could now track them. So if we wanted to study characteristics of humans, it doesn't make any sense to just look at adult photos. We would want to take snapshots of babies, adolescent, teenagers, and we could get a snapshot of them evolving throughout their life. Similarly, that's what we're doing with galaxies. We're looking at them at different time frames, and we're able to get a complete picture, not only of how they looked in their shape, but how they were moving right throughout the universe, so how they were being attracted, the collisions, because ultimately it's gravity, and now we are aware of dark matter as well that ends up attracting those galaxies and really setting the structure of the universe.